Okay, let's go ahead and get started. I think everyone knows that project one videos are due tonight at midnight. So there was some question about grade scope. Was Kishore, did we have an answer on that or?
Yeah, we send it off and it'll be done by the end.
Okay, so it should be done by end of class. We'll send out an announcement after class just so everyone knows. So it'll be set up so you can submit it. Are there any questions on that, either in class or on Zoom?
Yeah.
Okay,
So let's try that.
great.
All
Yeah.
members have to submit. It's fine.
Just one submission per group. Yeah. So yeah, and then on Wednesday we'll talk a little more about logistics for the question session. That's next week for the live groups. But just as a reminder, if you're not presenting live, then you will need to submit questions for the groups you're assigned to. I think it's by Friday this week, is that right? Or I forget when the due date is. There's also we'll send an announcement about that too, just to remind people. And I think that we just have them put it on the Google sheet. Is that right? Or there's going to be a Google form that they have to fill out. Okay.
We were like 2 or 1 minute report, like extra of the 12 minutes. Is that fine?
It should be fine. Yeah. I mean, don't go over like in general, the strictly speaking, we're only going to grade it based on the first 12 minutes. So, so if you're within like 30 seconds or so, you're fine. But if you're like 10 minutes over, then we're not going to count the extra 10 minutes towards your grade.
Only 2 minutes because of like Zoom technical.
Yeah, I think if it's clear that you tried your best, that's fine. Don't worry about it. It's more just we don't want to be looking at 30-minute presentations. That's to guard against that. Okay, so before we get started for today, are there any questions from last time? Okay, so I think everyone did like the score was like either 95% or 100% on the pre-lecture quizzes, so I think that's good. I did want to address one issue, which is there was one question about, when is it safe to go into the MRI scanner and with like keys and phone in your pocket, right? And I think one of the options was it's okay if the technician says it's okay to go in. So why is that not okay? Like, let's say I'm the technician. I say, yeah, go ahead. You can go ahead and go in there with your phone and your keys. Sorry, can you say that louder? Yeah, they may not know you have phone and keys. And what might happen to your phone and keys if you get too close to the magnet? Yeah, they're going to fly in. Okay. So no matter what anyone says, you are still responsible for your safety. Also, I think just as sort of something to think about for your own lives, like certainly when I'm getting an MRI done, which I think I've only had a couple MRIs for clinical stuff. Most of the time I've been in the MRI system is for research. But I'm always looking and seeing who's entering the room. So typically, if you have the option, you can have an option to have a mirror so you can see what's happening. Like what they'll try to get you to do is just watch a movie and have you just sort of relax and everything, and that's fine, but then you have no idea what's going on. So because I'm paranoid, because I know so much about the MRI system, I always want to have a mirror so I can see like, is someone entering the room carrying an oxygen tank? If so, I'm going to say, hey, stop. So I want to know what's going on because it is my life. So I think not that you need to be so paranoid as me, but just, something to think about if you're in an MRI scanner. It is one of the more dangerous places you'll be if someone screws up. Now, if everyone follows the rules, it's perfectly safe. You had a question?
Yeah, yeah. So, what if you want to image a person with some non-removable like metal devices like pacemaker or
Yeah. So that's something where there are different safety guidelines. And so certainly if there's someone with a metal implant or something, then there are sort of databases we look up to and typically, you know, like certain metal implants will be like if they're titanium, it'll be okay. And so we want to make sure that it's approved to be MRI safe. If it's not, then the person can't go in the scanner. But it's it's sort of we have to keep an eye on what's going on because like there's weird things that like for a while, a lot of people were getting metallic eyeliner and getting burns from that because the metal in their eyeliner would heat up And so we would have to tell people, or tattoos, right? Like there's sometimes metal in tattoos. And so we would have to tell people, screen people for that. And then I'm not sure it's a fad anymore, but there was a fad maybe just a year or two ago where people were having more electronics in their clothing, right? Does anyone experience have that? You know, like you have smart clothing and you have wires in your clothing. So if you have that and you're in the NMR system, those wires are going to heat up and they're going to burn you. So it's sort of we have to sort of keep track of what's going on. Um, the latest thing that came up with, more and more people are having like glucose sensors, for diabetes and things, and so we have to make sure those are MRI safe. So especially as more and more portable and wearable sensors become commonplace, that's something we have to keep an eye on because they may not be MRI safe. So yeah. So it's an evolving thing. So we every year we sort of have to see what's happening. Okay. All right. So today we're going to continue our discussion of MRI. We're going to review some of what we talked about last time, and then move on to sort of hopefully get you up to this place where we start to understand how MRI, we actually make images with MRI. This is just something that came across my news feed yesterday or so, and so this is from Nature, 7 basic science discoveries that changed the world. So MRI is certainly one of those. And this is a picture of Isra Rabi, who was a physicist from the 1930s, who was sort of one of the fundamental people to think about spin. And so these fundamental discoveries that happen are sort of the basis of what we're talking about. Okay. So just to remind you what we talked about last time, we spent a lot of time talking about the magnet and how the main job of the magnet is to create this polarization, this net magnetization that we're going to work with. Okay. Then we also talked about excitation. And so the idea is that because this magnetization, if it's always rotating around the main field, but if you can sort of see here, this isn't really a time varying magnetic field as far as you can tell, right? So it's going to be very hard to sense that this is rotating around its own axis. I mean, there are probably methods to do it, but it's not an easy thing to do. So what we want to do is we want to take that magnetization and tip it away from its equilibrium. So now it's going to precess. Okay, so this is a magnet that's moving like this. And so you can imagine if you're a coil over here, you're going to sense a time-varying magnetic field, right? Because the magnetic field you feel from this is going to change as this thing is moving. Okay. And so therefore we can just use Maxwell's equation, E is proportional to dB dt, and that's the basis of our sensing. All right. So the RF excitation is the process of how do you tip that magnetization away? Okay. We'll get into encoding today is how do you start making an image? And then we might talk a little bit about integration, which is sort of what the receiver coil is doing as well. So just to remind you, equilibrium magnetization is because spins tend to align with the main field. That's the lowest energy state. So the probability of finding spins aligned with the field is much greater than having them anti-aligned. Now, spins can have sort of different orientations. So just on average, the spins line up to give you the magnetization. We talked about precession. And so the idea is if there's a magnetic field pointing up, there's going to be precession going around. And so to remember the direction of precession, this is basically the left-hand rule. Okay, so if you curl your fingers and your thumb is pointing in the direction of the main field, the direction of precession is the direction of where your other fingers are pointing. Okay, so it's the left-hand rule. All right. The other important concept we talked about is the Larmor frequency. So the rate at which the spins are going to precess, and that's going to be omega equals gamma times b, or if it's in hertz, is f equals omega over 2 pi equals gamma over 2 pi times b. Okay, so often in this class, we're going to give you gamma over 2 pi. All right, so then you can just take gamma over 2 pi and multiply by the main field, and you're going to get the precession frequency in units of hertz. All right. I think that was one of the pre-lecture quizzes where you had to look at the frequency at the Earth's field. And I think almost everyone got that. Okay. Okay, and just to remind you that even in right now, sitting wherever you're sitting, either you're in class or you're somewhere else, on Zoom land, we are all in the Earth's magnetic field. Okay. And in fact, I'm not sure what the inclination is of the field here, but your spins are all processing around that main field at, I think we decided it's about 2000 hertz. Okay, so 2000 times per second, your spins are processing. Okay, and so in fact, if you didn't want to spend money on a large magnet, or you want to set up an MRI system that you could take out into the field, like in an emergency, these are some examples of magnets that just work on the Earth's magnetic field. Okay, and so they don't require that main magnet. They're just using the Earth's field as a magnet. And then the next thing we talked about was RF excitation. And so the idea is that once again, we're trying to get away to tip this equilibrium magnetization away from its equilibrium state. And because things are can process, as we tip it, it's also going to process. So the tipping and precession happen at the same time, especially if we're in the laboratory frame. Okay, so what it looks like is this. Uh, so everything's processing, right? And it's sort of the main, as they're tipping away, it keeps processing. So it's really the main net thing just appears as the arrow being tipped away from its equilibrium state. And then so here, if we're on, we talked about the importance of being on resonance. So if we apply the energy at exactly the resonant frequency, then we can very efficiently tip the magnetization away. If we're off resonance, then the magnetization is not tipped away. It sort of stays where it's at, right? Because we could be putting a lot of energy into the system, but if you're not on resonant, it's not going to have an effect. Okay. It's just going to heat up your subject. So it's sort of a waste of energy. All right. The other important concept is that because it's sort of complicated to think about things rotating all the time, it's going to be much easier if we think about things in the rotating frame of reference. All right. So the example that we talked about is if you are looking at someone on a merry-go-round, it looks like they're going around. And so to describe their dynamics, you always have to describe this going around. So if all you care about is are they standing up or are they vertical or horizontal, you don't really care about this going around. So it'll be much easier if you imagine stepping onto the merry-go-round. So now you're in the same frame of reference they are. So then their dynamics become very easy to describe. All right. So that's shown here, where on the left here, we see sort of the magnetization, the tipping is this very complicated spiraling down. Okay. But if we go to the rotating preference, it's simply the magnetization is just going down like that. Okay. So it's a much easier dynamics to describe, and that's shown here in this picture here. Okay. And you can sort of see if the blue cyan is showing the B1 field, and if I curve my fingers and point in the direction, then the direction of precession is this way, right? Okay, so that's the cyan thing is pointing this way, and so you sort of see the magnetization processing this way, right? Because it's following the left-hand rule. Okay, so that's why it's doing that. Yeah, question.
Like, would the B1 field just be emitted pulses, like pop, 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 pop?
Sorry, can you say that again?
So cause this tipping, the B1 field isn't actually spinning with our proton, so do you need to like time it sort of like move it?
Yeah, that's a great question. So the way the B1 field is literally we just have a coil and we put in a sinusoid that's going to create a time varying magnetic field. So it's going to have the frequency of that field that it creates is at exactly at the Balmer frequency. So it's all done electronically. Yeah, because you can't have something spin at 127 million times per second, right? It would just blow up. Okay, that's a great question though. I mean, if you could design something like that, let me know because that would be pretty amazing. All right. Um, so where we get to is this flip angle. And so basically, in the rotating frame of reference, there's no B0 field, right? Because if there was a B0 field, we'd have precession. But we're saying we're in the rotating frame of reference, so it's as if there is no B0 field. So all we really see is the effect of the B1 field. So this is the B1 field pointing this way. And we know from the left-hand rule, we're going to have precession going around the field, okay? So that's that tipping, right? So we know that the frequency of precession is going to be omega 1 equals gamma times B1. Okay, so that's the rate. That's in radians per second, right? So if I apply a field for amount of time and I want to know what's the net angle, then I simply have to take the integral of omega 1, right? For some time t, okay? And so basically, because if you think about integrating radians per second over seconds, you're going to have something that's just in radians, right? Okay, so integrating that is what we're trying to do. And so we can sort of see that then that, so our flip angle is essentially how many radians have we flipped it away, okay? So then we can rewrite this as theta equals gamma times the integral of the B1 field, okay, over some amount of time. So that means whatever waveform I give you, I just have to figure out the area under the B1 curve and multiply it by gamma, and that'll give you the flip angle. All right. So that's, I think we'll be posting a homework uh, after the projects are due later today. And so there'll be a very simple question, pretty much similar to this question. So if you understand this, the homework should be pretty easy. So let's just go over this. We went over this yet last time at the end, but let's review that today. So here we have the RF pulse that looks like this, right? It's of amplitude A and it's a sync, so it has its first zero at T, okay? And so this is our B1 of T, right? So what we said is we need to know the area of that, okay? But it's a sinc function, so it's like a sine x over x, and integrating that we know is going to be sort of, you can do it, maybe you need to do an integration of parts or something, but it's going to take a while. So if we're lazy, we're going to say, oh, well, I remember the definition of the Fourier transform. I can say, I know that if I took, say, the Fourier transform B1 of f, let's just call this little b, just to keep that separate, is equal to B1 of t e to the minus j 2 pi f t dt, right? That's the Fourier transform of the B1 field, okay? And what if I actually evaluated f equals 0? Then B1, the Fourier transform at 0 is just going to equal B1 of t dt, okay? So that's a nice property because if you're looking for the area of a function and you just happen to know what this Fourier transform is at 0, then that's something. And we're going to see this later in the lecture today because this is what we mean. This is called the center of Fourier space or the center of K space. So the center of K space, center of Fourier space is really, really important because it basically tells you the average value of your signal. Okay. So if you look at an image and it's really bright, its Fourier transform at 0 is going to be pretty high. Okay. If you look at it something and it's got a very low mean value, not very bright, the average value, but the value of its Fourier transform at 0 is going to be very small. All right. So that's an important thing to keep in mind. And we'll revisit that in about, say, 30 minutes or so. Okay. So now we know, now I just need to know the Fourier transform of a sinc function, right? So we're given that we have our sinc function is A sinc t over t. Okay. But we know that a sinc function Fourier transform just gives me a rect function of f, right? And then by the scaling theorem, I can write that this is a scaled version of it. So it just goes to a times t rect of f times t. And if I evaluate this at f equals 0, it's just a times t rect of 0. Okay. So what's the value of the rect function at 0? Anybody? What's the rect function look like? It's just like it goes up and comes down. So what's its value? 1, right? So this is just a times t, right? Because that's just the rect function of 0 is just 1. So I know that I can say, oh, okay, well, I know then this area is just equal to a times t. Okay. And then I know from my previous slide that, my flip angle, I want it to be 45 degrees. So that's pi over 4 radians. It's equal to gamma times the area, right? And in this case, you're asked to solve for A. So I just say A equals gamma over pi over 4 times, what is it? T, right? Everyone got that? Right? Is that right? Yeah. Oh no, I got that wrong. You guys need to correct me if I'm wrong. Okay. Let me see. It equals pi over 4, right? Over gamma times t. Is that right? Okay. So then we also know that that's just pi over 4 over 2 pi times, we're given gamma over 2 pi is 4,000. So put the 4,000 here. And then we have 250 times 10 to the minus 6. Okay. Let's come down here. The pi's cancel out. So I get 1 over 8 times 4 times 10 to the 3 times 0.25 times 10 to the minus 3, right? Equals 1/8. Okay. So I get like 0.125 Gauss, which so the closest answer would be 0.12 Gauss. So it's basically high school algebra, or depending on when you learn this, sixth grade algebra, something. So everyone can do this. It's just a matter of putting together the pieces. Okay. Yes.
A little bit on, but I thought this is the Fourier transform of Rex gives me C.
Yes, that's right here. It goes both ways. That's the duality theorem. If you know one way, you know it the other way. Okay, so
And that both ways, like if I know the frequency at 0, like I just know the integral. Okay.
yeah, if you know the frequency at 0, you know the integral, and if you know the frequency, if you want the integral of the Fourier transform, you just need to know the value of the function at 0. Yeah, so everything goes both ways. Yeah, so obviously we're not expecting you all to be experts on the Fourier transform, but there will be some basic things that we need to understand just so you have some intuition. So yeah, and I think there'll be some basic Fourier transform questions on the homework that's coming up as well. So that'll help. Okay. And then those reference a video on Fourier transforms that you can look at as well. All right. Okay, so let's work through some math. So any questions before we move on? Okay, seeing none on Zoom land, we'll keep going. So what we want to do is build up some of the mathematics just so you have sort of the underpinning of it. So we said that the general form of the dynamic equation that we're looking at is the magnetization follows this. The dm dt is equal to m cross gamma b. Okay, and that just describes precession, right? So this is just saying in a B field, okay, that's pointing this way. And if I have the B field this way, I have my M vector this way. M cross B, once again, that is still the left-hand rule, right? M cross B, right? So that's going to give me the direction of the cross product. Okay. Everybody remember the cross product from high school or junior high? Okay. All right. Oh yeah, it's the right-hand rule. Sorry. M cross B. You got it. Yeah. So it's one of those, right? Okay. So yeah, it's the right-hand rule, M cross B. So, and then you can write that. You may remember that you can write the cross product as a determinant like that. And then this just gives you the formula for how to write the cross product in terms of the I, J, K components of each vector. All right. So we're just getting it into sort of a form where you can look at it in the coordinate system. So that means we can write it as what's the derivative of the mx component? Yeah, question.
So why are you using the left hand position and right hand rule on this?
Yeah, it's just because it works out. So basically, if I want to know the direction of precession, I just take the left-hand rule, which is consistent with the right-hand rule for the cross product is just math, right? And this is because this is the equation of motion. It's saying, like, if it was minus m cross gamma b, then it'd be the right-hand rule. But because of this is the way the mathematics works out, it's a left-handed precession. Yeah. Okay. It's not actually, let me correct it. It's not the way that's the mathematics works out. That's the way nature works. Okay. Just nature has decided it's going to be that way. All right. Just the same way, like if I have a current, the B field is, dependent on a certain rule, right? That's nature decided that, right? Okay. Okay, so I have this equation of motion. So three linear equations of motion, first order linear equations. I have dmx dt, dmy dt, dmz dt, and they depend on both the magnetization and the B field. So I can write this as this matrix equation where I have on one side the mx, my, mz components, and in the inside I have the B field. So what you'll notice is all the elements on the diagonal are 0. Okay. So all I have are off-diagonal elements of BZ, BY, and BX. All right. So we're going to look at the simplest case where I only assume I have a BZ component. All right. But before we get there, has everyone heard of the term phasors? Anyone? Okay. Okay, good. And everyone heard of Euler's identity? Okay, good. So basically, this is Euler's identity, and J, because we're engineers, is equal to square root of -1. Okay. Um, and so basically, this is probably one of the most important things to keep in mind for not only this class, but a lot of science, is we can conveniently represent a lot of physical phenomenon using these phasors. Okay, because in nature, things rotate around a lot. Okay, things are always oscillating. And so if we have a convenient way to represent that, then we're in pretty good shape. So just to remind you, what e to the j theta looks like is we're representing it as its real and imaginary parts. Okay. So, and the other thing is the magnitude of e to the j theta is 1, right? So it's just this vector that has magnitude of 1 and just goes around and around. And so literally all we're saying is that the theta just tells you what the angle is between the vector and the real axis. Okay. So because we said we're doing clockwise precession, okay, because of the right left hand rule, it's going to be typically the precession is going to be negative angles, right? Because that's going this way, the angles can become more negative. So for example, here's theta equals 0, minus pi over 2, pi, and pi over 2. So this represents sort of as we're going in a clockwise precession, the angles become more negative. Now we'll see later we can also do counterclockwise, and then the angles will be positive, right? So the reason to do that is because we don't really, this is sort of bulky to deal with. And if we just look at here, we've got rid of, we've said bx equals 0 equals by equals 0. So the only components we're left with are we're talking about what's precession when I only have a B0 field, all right? And in this case, we see that the dmz dt is nothing happens, right? It's just equal to 0. So this is just dmz dt equals 0, which means mz is not going to change, all right, in this situation. So all we have to look at is sort of these two basically coupled first order differential linear equations, but an easy way to solve it is we just define a complex magnetization, which is mx plus j my. And this is what we're going to use for the remainder of the course, because we're going to think about spins as these complex vectors that are just spinning, okay? Otherwise, you have to keep track of mx and my, and it's sort of like you have double the work. So we're sort of want to be a little lazy and just say, hey, what we really care about is where is the spin? So we're going to find this complex phasor. And then if we plug that definition into this, we get this. And this is just a first order differential linear equation, which is dm dt equals minus j gamma b naught times m. All right. And this is something that, everyone can solve. We know the solution is just going to be something where it's going to be m of t is equal to some initial condition times e to the minus j gamma b naught of t, right? Because if you integrate an exponential, you just get the exponential back, right? So it's very simple. And so therefore we get and then we have this gamma b naught, but we know that that's just the Larmor frequency. Omega naught equals gamma b naught. All right. And so this is the most probably the first really important concept to keep in mind is this just says that this is our mathematical description of precession. We've talked about it physically, the spin precesses around the main field. Now we just want a mathematical notation so we don't have to just talk about precession with words. We can actually say mathematically, this is what we mean. Okay. So look at this. This just means that this has the form where theta equals minus gamma naught t, right? It has the form e to the j theta, right? So this is just something where this angle is just theta equals minus omega naught t, which is exactly what we want. We want this clockwise precession, right? So this is describing free precession in the presence of a magnetic field. Okay. So this is essentially just, we've just done all this work to say, okay, I can very complexly describe this physical phenomenon that I see, right? And that's the basis for setting up what we need to do next. Okay, so now let's sort of get into some of the more of the physics and what happens in the MR experiment. So this part here is, we're talking about from here to here is excitation. Okay, so here I put a pulse at Larmor frequency. Okay. Okay, so I essentially this is applying the B1 field, and you notice that causes the B1 to tip from here to here. So here I applied an angle of theta equals pi over 2 because I flipped at pi over 2 radians. All right, so I left that pulse on long enough such that the area of that pulse allowed me to tip pi over 2. Now, the next part of the MRI experiment is we just turn off things and we just listen. And so what happens is those spins process and they keep processing, right? But what actually happens is, as everyone knows, nothing lasts forever, right? This spin wants to always go back to here, right? So that's what we're seeing here. This is the return to equilibrium, right? We've taken this from a low energy state into a high energy state so it can process. But everything in nature is going to make this go back to its lowest energy state, which is here. And so what we're going to see is if we look at the signal as what you're showing, the NMR signal is the signal from this guy. First, it's very strong, and then eventually it goes back to here. Okay, and so therefore you're going to see this decaying exponential as the received signal. All right. So that's what's called the free induction decay. All right, and we can look at it as sort of a function of time. It's just going to decay away. So there's this exponential decay. And as it's decaying, it's still sort of processing at, processing at omega naught, right? And so we think about it as a magnetization, right? This magnetization is just sort of getting shorter and dying away. Okay. So we're going to talk a little bit about relaxation, just so you know about it. And then what we're going to do is later in the course, we're going to come back to this relaxation and take a deeper dive. But for today, we're just going to just let you know that it exists and that we need to take into account. So magnetization or relaxation is just the process of going from here back to here. Okay, so things are relaxed back to their lowest energy state. So there's two types of relaxation that you need to know about from MRI. There's T1 and T2, and they sort of have different mechanisms, and we'll talk a little bit about why that's important. So T1 is just the return to this equilibrium state. Okay, it's just saying that here I have some m sub z component. Here I have 0 m sub z component, right? So it's the growing back of this component back to its equilibrium state. That's T1, right? T2 is just the fact that this component here is going to die away. Okay. And it turns out these are related, but they're not exactly the same. Yes. T2, the transverse component. So the transverse component. So the MXY component. So this will be called longitudinal component. So the m sub z is this component. It grows back. And the MXY is the transverse that decays away. We'll look at some pictures of that. So the m sub z follows this longitudinal relaxation. It just grows back exponentially. So if I set it to 0, it's always going to go back to its equilibrium state, which in this case, it's going back to say some m naught. Okay. And this is just, you can think of this as things always want to go back to the equilibrium state. So why does this matter? It turns out that it matters because different tissues have different T1s and T2s. And so one of the ways clinically we make different types of images is we say, okay, I want to differentiate like muscle from brain, from kidney, from fat. And so because different tissues recover at different rates, we can take advantage of this. Okay. So this is showing the T1 values at different field strengths. And so it's this contrast, just the same way in CT, we make contrast because different things have different attenuation coefficients. In MRI, we take advantage of the fact that they have different relaxation rates. Okay, so later on the course, towards the end, we'll get into how you actually take advantage of that. The other thing is the M transverse decay, which is what happens to the MXY component. And so remember in the rotating frame that we're just going from here to here, right? We're not worried about this. So that's just this component shrinking down back to zero. Okay. And this basically is due to the fact that um, at different the spins can talk to each other and sort of things that dephasing of spins, sort of things get out of sync, and that's what leads to that. Okay. And we'll get into that in more detail later, but that's sort of the primary thing where this exponential decay we're seeing. So the signal we're depending on to create the magnetization is decaying away with this exponential decay. Okay. And this reason this is important is different tissues have different T2s, okay? And therefore we can take advantage of that to make different contrasts. Yeah, question.
Different things. Like if I know T1 donut.
Yeah, we'll get into that, the physics of that later, but just that's the way nature works. Yeah. So a lot of this is just people have done experiments and they've characterized these things, and we'll get into the mechanisms of that later. Today, we're just making sure you understand what's going on. I mean, I at least have a very, very, very quick intro to them. So the idea is that when we tip the magnetization here, like if you think of all the spins in a given voxel, there's a million of spins. And if you can imagine them processing at different rates, then essentially instead of them being all aligned, they sort of get out of phase, right? It's sort of like if I had all of you running around in a circle, I start you at the same speed, but after time, some of you get tired and you lag behind, and some of you are really energetic. You've had a lot of coffee and you run ahead. At some point, you'll all be distributed around the circle, right? So if I took the vector sum of all those positions, I'd get zero. And that's essentially what's happening with T2 decay. And we'll go into that in more detail later. So anyways, this all leads to this imposing thing called the Bloch equation, named after Felix Bloch, who shared the Nobel Prize for discovery of NMR. We've already done this part. This is the precession part. And so this is just adding on something that describes the decay in the MXY, and you can sort of see this only affects the MX and MY components, and this that describes the effect on the M sub Z, and you see this only depends on the M sub Z component. So this is going to fill in the diagonal terms of that matrix, because the diagonal term determines the decay. Okay, so it looks like in matrix form is you're sort of seeing these decay terms along there. Okay, so this is more just for your edification, just so you know where it's coming from. And then where are we going? And then just to summarize, what that means is that the Z component is always you're always going to see some recovery to the M sub zero equilibrium state. Now, an interesting thing is, you remember this magnetization, right? Here, in this case, I've tipped it to here. So the M sub Z is zero, right? But if I just kept applying B1 field, I could tip it all the way here, right? Where it's negative, right? And now it's got to recover from negative to back to its equilibrium. So I could have started at minus M sub zero, and then it recovers like that. And guess what? As it recovers, at some point, it crosses zero. So why might that be useful? If I have some species and I tip its magnetization, and as it recovers, at some point its magnetization crosses zero. If I image at that point in time, I've essentially erased that. Okay. So for example, if I had an image with a lot of fat in it, and I said, I want to see what the body looks like without all that fat, it means I could tip the magnetization and then image it at the point where fat crosses that part. And then my image will have no more fat in it. Okay. So that turned out to be really useful clinically. And we'll look at some examples of that later. So at this point can erase tissue, right? And then this is the the transverse component, and it sort of does this death spiral where it's sort of it starts off with some magnitude, and it sort of just, if you're thinking about its precession, it just decays down like that. Okay. So this is a nice sort of movie that sort of summarizes that. What you're going to see on the left-hand side is sort of we're spiraling down the transverse magnetization. In the middle, we're looking at its magnitude, and then we're also going to see M sub z recover. So just watch this. And so what you'll notice is the transverse magnetization typically dies away much more quickly than the longitudinal magnetization recovers. All right. Look at it one more time. Okay, so that's relaxation in a nutshell. And so this is another picture of that. In past years, we've given a for homework assignment on this. So we'll skip that for this year. So the bottom line is why it matters is that this is an image I showed earlier where it's the same brain, but just taking advantage of the fact that different tissues have different T1s and T2s. And what we'll see later in the course is we can manipulate our imaging timing such that we can either enhance or diminish, the amplitude of a certain tissue. Okay, and that's done by knowing what the T1s and T2s are. So if you look at this, this is in brain. This is cerebral spinal fluid, gray matter and white matter. They have different T1s and different T2s, and therefore we can take advantage of that to create these different images. All right. Okay, so that's sort of excitation and relaxation. Now let's get into encoding. And this is where we talk about the MRI gradients. And this is going to be sort of, we're going to spend a couple of lectures on this because this is sort of the heart of how imaging occurs. And so remember the gradients, we're going to have three gradient coils. There's an X gradient coil, a Y gradient coil, and a Z gradient coil. And their job is to create linear gradients in the magnetic field. And the key is that spins persist at the Lamarr frequency. So omega equals gamma times B. Okay. Previously, we said, okay, well, there's a main frequency, omega naught equals gamma times B naught. Okay. Now we want to extend that and we want to say, well, what if my B field is something like B naught plus some delta B? Okay. Then I would know, well, my frequency is equal to omega naught plus some delta omega, right? Where this delta omega equals gamma times my delta B, right? So what this means is I can make spins. Spins don't have to just precess at some frequency, gamma times B naught. If I put in the right field, I can make a spin here precess differently from a spin here. Okay? And if I can make different spins precess at different frequencies, then that's going to give me a chance to create an image, right? Because to create an image, I have to know, well, how much tissue is here and how much tissue is there, right? And how's that different from here, right? So this is sort of building up that idea. So spins at different physical locations will now precess at different frequencies. And now we just have to keep track of what does that mean and how do we take advantage of that. So here's the interpretation. So here I've applied a linear gradient in the X direction, right? So this means the field's getting stronger as X gets more positive, and it's getting weaker as X is less positive, okay? And so it means spins out here will precess faster, okay? They're going to go clockwise much faster, and spins over here are going to go slower. So they're going to precess still clockwise, but at a slower rate, okay? So that's shown here where, oh, the other thing is that, before I do that, and the spin sort of at this here is very important. This is what we call the isocenter. Okay, so the isocenter is sort of the middle of the magnet where we assume that there's no added field. Okay, so everything at isocenter, we assume B is equal to B0. And spins there precess at gamma times B naught. Now here's where we're going to go into the rotating frame right away because we don't really want to have to keep track of these are all spins spinning at different rates. So what we're going to say is, well, let's pick the isocenter as the place, that's our rotating frame, right? So those spins in the rotating frame aren't spinning at all, okay? So in fact, if I go out here, these spins were spinning faster than isocenter. So relative to the isocenter, those spins are going in a clockwise rotation, right? Okay, so these will have a clockwise rotation in the rotating frame. Similarly, these spins are spinning slower as opposed to the isocenter. So relative to the isocenter, they're actually going back this way, right? If it's sort of like if you're running faster than someone on a merry-go-round, it appears as if they're going backwards, right? So they're going to have a counterclockwise rotation, right? So these are going to appear counterclockwise in the rotating frame. Yeah, question. It's like the center of the magnet. Um, the isocenter would be actually on a magnet on if you want to use that analogy with a merry-go-round, it would be someone who's just standing on the merry-go-round. And then the spins going faster are they're running around the merry-go-round in the direction of the merry-go-round, and the spins that are going slower are running opposite to the merry-go-round. Yeah, right. Because the rotating frame defines in the merry-go-round, that's the rotating frame, right? If you're not moving with respect to the merry-go-round, you're the isocenter. Right. So yeah. So like you've all done this as kids, right? You can be on a merry-go-round and you can run with the merry-go-round or you can run against the merry-go-round, right? Similarly, like on an escalator, you can like go with the escalator or you can go against the escalator, right? So that's and if you're just standing on the escalator, you're in the frame with the escalator, right? Okay, so this just shows you a picture of that. So basically what we're seeing here is we're seeing, let's say this is the x direction. So we've applied a gradient in the x direction, right? This is isocenter, right? So not those spins appear static, right? They're not spinning around. And you can sort of see here, these are going like clockwise and these are going counterclockwise, right? So we know that this is a positive delta B and this is a minus delta B, right? Because the spins on the left are going clockwise, they must be going precessing faster. So they have a stronger field, and the ones on the right have a weaker field. Okay. Similarly here, here's the isocenter here. Okay. So now we've applied a gradient in the y direction, right? So these guys are going to counterclockwise, and these guys are going clockwise, right? So we know the field is stronger in the negative y direction. So here we would say the gradient is negative, right? Because as we go in the positive y direction, the fields are getting less. And here we would also say, in this case, gx is less than 0, right? Because the gradient is such that as I go in the x direction, negative x direction, the fields are getting stronger. Okay. And then the cool thing about MRI is you can actually apply gradients in both directions at the same time. Okay. So notice here, these guys are going counterclockwise, and these guys are going clockwise. And if you look at the equilibrium points, they're along these diagonals, right? Everything along a diagonal is spinning at the same rate, okay? Because I've applied both the gradient this way and this way, so it's going to spin faster as I go this way and also this way, right? So that's what we're going to get into with MRI is how do we actually think about, even though we start off with this very simple concept, it starts getting complicated pretty quickly. So we need a way of sort of how do we encapsulate all that, okay? Okay, so I think what I'll do is I'm going to skip this example problem. We'll come back to it later. So, because I want to keep sort of the momentum of going on to this rotating frame of reference. So I want to just give you a sense of what things look like and how do we actually create an image with MRI. Okay, so here's the idea and then start relating that to Fourier transforms. So what we're showing you here is we're going to use these mannequins. In the days before Zoom, we used to do this in person and have more in-class demonstrations. Now that we're in Zoom, I've gone to these virtual things. So this person going around is representing your spin. Okay. All right. So if in the days before Zoom, I would basically have people stand up in front of class and like rotate. Okay. But now we're just going to have this. So is this person, so the B0 field is pointing in here and the person is rotating around it. So they're processing correctly, right? because they're doing this left-handed precession, right? But in the rotating frame, the person would just be static, right? There's no net rotation, right? Okay. And so we did this, we're going to do this experiment where Erwin Hahn was a very famous physicist at Berkeley who died, I think, a couple years ago. And a famous saying he had is there's nothing that nuclear spins will not do for you as long as you treat them as human beings. Okay. And this means that a lot of what MR physicists do is we sort of think about what spins are going to do. And we sort of, okay, well, this is, if I do this, this is what the spins are going to do. And you almost have to think like what the spins are going to do. Okay. So here's the experiment we're going to do. We're in the rotating frame, and we're going to imagine that this is the x coordinate system. Okay. And this is the isocenter here. All right. And so the experiment is we start off with all the spins aligned, okay, in the same direction. So we can imagine if these represent spins, the way they're facing represents the alignment of the spin. Okay. And then, and the B0 field is pointing this way. Okay, so these are sort of our human spins to sort of get across this idea of what's happening. Okay, so now what we're going to assume is we're going to apply a gradient like this. So this is my GX gradient. Okay, so that means the spins here on the right side are going to spin faster than the spins on the left side. Okay, so let's see what happens if we do that. And so the next stage, we're going to look at this. So this one is still at isocenter, so he didn't spin at all, right? Because there's no added field there. This one, what's the angle that this person rotated? It was facing this way and it turned how many degrees to the right? 90. So this would be pi over 2, right? And we'll assume this one went twice as much, so it went pi. Okay. What about this person? What would be the angle of rotation for this person? Yeah, minus 90, minus pi over 2. And this person is minus pi. And in this case, we're seeing sort of the ambiguity, right? Because you can't really tell pi from minus pi. But because we know which way the gradient was, we know this person must have gone minus pi. Okay. So now let's look at the next question. If we look at the orientation of those spins, can you tell, like, what's the period of variation? Like, how far do I have to go? Let's say this distance between people is delta x. How many delta x's do I have to go before the spins are pointing the same way? So what's the period here? Do you guys see any two spins that have the same orientation in that row? Okay, so yeah, I have to go all the way, right? I have to go from this guy, so 1 delta x, 2 delta x, 3 delta x, 4 delta x. So the period before delta x. Okay, so there's basically, by allowing these spins to rotate for a certain amount of time, I've established some sort of variation in their orientations. Now I let the spins play out some more. So this is still at theta equals 0. This one has gone another pi over 2. So now this is at pi, right? This one has gone another pi, so it's back at 0, right? This one has gone another minus pi over 2, so it's at minus pi. And this one is at back 0. Okay? So I just let them keep spinning at different rates. Okay. So now at this point, what's my period of variation? How far do I have to go between spins to get before they look like they're pointing in the same direction? 2 delta x. Good. So now the period is 2 delta x. Okay. So you can sort of see by just applying these gradients and letting the spins do what they want to do, I'm going to get some variation in the pattern. Okay. And then here, this is still theta equals 0. This has gone to theta equals minus, oh, sorry, this should be, I got these wrong. This should be plus, this should be plus, this should be minus, right? Is that right? This should be minus pi, this should be plus pi, because it's going in clockwise rotation. And so this should be minus 3 pi over 2. This should be, once again, minus pi, I suppose. This is at plus 3 pi over 2, and this is at theta equals pi. Okay, so here the period is back to 4 delta x. So in this case, we've gone back there. And if we go here, what's the period here? So we're back now to the original state, right? All the people are pointing in the same direction. Did everyone see that? Okay. So what's the period when everyone is pointing in the same direction? There's no variation, right? So essentially the period is infinite, right? Okay. So we'd say this period is like infinite. And let's talk about the frequency. So the frequency is kx, which is equal 1 over the period. All right, so we're going to introduce this concept of spatial frequency. So that would be 1 over 4 delta x here, 1 over 2 delta x here, 1 over 4 delta x here, and 1 over infinity is 0, right? So by zero frequency, we mean things don't vary with space, okay? And so this also gets to when we talked about the center of K space, zero frequency means that's where there's no variation, all right? So that's what we mean by the center of K space. Okay, this is just another example of that. I don't think we need to go through that, just showing that. Okay, so let's sort of start adding some math to this. So remember, we're going to go back to our phasor diagram, and now we're going to tie this to Fourier transforms. All right, so this will be somewhat of a review, but some new material. So remember, the Fourier transform is defined as if I have some function g of x, I multiply it by e to the minus j 2 pi kxx, integrate over dx, and that gives me the Fourier transform at some frequency kx, where this kx is this thing, okay? And this is just the form where theta, this is as exponential, where theta is equals minus 2 pi kxx. All right, so this means that all I've done is I've taken my function, I've multiplied it by a bunch of phasors, okay? Where the angle of the phasor depends on where I am in x, right? Because at some given value of kx, as x changes, it's going to change the angle of the phasor, okay? So let's look at that. So let's assume kx equals 1. At x equals 0, theta is equals 0. So that's sort of where we started off with in that experiment, right? Now let's move along. Some x equals 1/4. This means 2 pi kx x equals pi over 2. So theta is equal now to minus pi over 2. Okay. So this would have been like a spin that was going a little faster, right? Similarly, if I go out to x equals 1/2, 2 pi kx x equals pi. So in this case, theta equals, this would be minus pi, right? Which is equal to pi, which is fine. But just to keep the sign there. And if theta equals 3/4, 2 pi kx x equals 3 pi over 4. So theta would equal minus 3 pi over 4, okay, which is equal to pi over 2. Okay. So what we're seeing is we can use this complex exponential to describe exactly the phase of every spin. Okay, and that's going to be the link between the math and the physics. Okay, so here's the interpretation. So basically here, this is our starting point before, right? Where all the spins are pointing in the same direction. Okay, and we said that corresponds to zero frequency. So that's kx equals, whoops. That's kx equals 0. And let's see if that works. If I put e to the minus j 2 pi and I put this as 0, right, that's kx, then that just equals 1, right? So these are all theta equals 0, right? So that makes sense. That's just saying if I'm at zero frequency, then all the spins point in the same direction. So that works. Now let's go to this one where kx equals, so kx equals 1 over 8 delta x in this case, right? So if the frequency is 1 over 8 delta x, what's my period? Just 8, yeah, 1 over that 8 delta x. Let's see if that makes sense. In this case, this is delta x, right? Let's say. So I can see if I go 4 delta x's, I've gone from up to down, right? So half a period is 4 delta x. So that makes sense. One period is 8 delta x. So that works too, right? That gives me the right answer. Okay. And similarly, if I go to, sorry, got kx equals 2 over 8 delta x equals 1 over 4 delta x, then that period is, that frequency corresponds to the period of 4 delta x, right? And let's see if that works out. Then if I go from here to here, that's 4 delta x, that's one period. Okay, so that also makes sense. I've got something that has a period of 4 delta x. All right. Okay, so what we're doing is we sort of said, okay, this physical picture, we have spins going in different things, going at different rates. It seemed like the important thing was to keep track of what angle they're at as a function of space. Now we're going to take a sort of a related sort of tangent to sort of, we want to tie this to Fourier transform. So we're going to review a little bit of how we think about Fourier transforms. All right. So here, once again, are the definitions of the Fourier transforms that I think Professor Buffet showed to you. So if I have some function g of xy, I can take its Fourier transform. And notice all I'm doing is I'm multiplying by these complex exponentials. Right? So now we want to just take a step back and look at that. And just as a note, that Prince and Link uses u and v instead of kx and ky. We'll exclusively use kx and ky because if you read the MRI literature, that's what people do. I'm not really sure why they chose u and v, but it's a simple substitution. Okay. All right, so this is gonna be a little bit related to the homework assignment you did. So we're just gonna try to reinforce some of the concepts. So in a lot of imaging, we talk about image space. So that's sort of the space of your image. And the Fourier space we'll talk about as K space is typically how we refer to it in MRI. And for this course, we're only going to do two-dimensional Fourier transforms. You could do three-dimensional, four-dimensional, any n-dimensional Fourier transforms. But to keep things simple, we're just going to do 2D because that's the minimum you need for an image, right? You need 2 dimensions. So we're going to have a kx dimension and a ky dimension. And so this is the space that we collect the data in MRI. We actually collect the data in Fourier space. And we take all those numbers and you can store them in MATLAB or Python or whatever. And then once you've got that, it's pretty simple. You just do an inverse Fourier transform and you get your image. And that's literally all you're doing. Okay. So what we want to understand is, well, how is the data? Why is the MRI data in K space? And once you do that, then all you have to do is it's one line. You do IFFT and you've got your image. Okay. Okay. So one of the important things we talked about is the center of K space, which we went over, which is the area of the function is just the center, is just the center of K space. So that's good. So center of K space is the area under the curve or the mean value of your image related to that. Here's the more important thing to think about, which is what do these complex exponentials mean for images? Okay. So I can write this complex exponential from Euler's theorem as a cosine that depends on both kx and ky plus j times a sine that also depends on kx and ky. All right, so let's look at what that means. Let's say I have a case where ky, let's just look at the cosine term, okay? Let's just focus on this term. And let's consider the case where ky is equal to 0, right? So ky equals 0 means there's no variation in the y direction, right? Because there's no frequency at 0 frequency. So all my variation is only in the x direction, right? So if I thought about an image, like an image might look like this. It's going to be very bright, like it might be bright and dark and bright. So it's like bright, dark, bright, dark, bright. Okay. So this might be sort of an image that I would get that would have a cosine dependence. So essentially like a zebra stripe, right? Anything that's stripy is going to be like a Fourier component. And so these lines here just represent the peaks of my cosine. So cosine 2 pi kxx is such that the peaks are spaced at 1 over kx. Okay? So basically this is the period, right? So if you think about things in the kx dimension, those represent stripes going this way. Okay? Now, if I look at something that's got a kx equals 0, that means there's no variation going this way. So it's going to be an image that only has variation going up and down. All right. And so that would be cosine 2 pi kyy. And here, this period is just 1 over that thing. Now, the important thing is images aren't just made up of, if you look at an image, any photo or anything, it's not just, things don't just vary this way or this way. Things can vary in lots of directions. So I also need Fourier components that have both kx and ky variation, right? And so here's an example of something that both varies in the x and y direction. And it turns out that the spacing here is now 1 over kx squared plus ky squared, square root of that, okay? And a simple way to think about and where you are in the Fourier domain is if I give you on a homework assignment or something, if I give you a point in K space, okay, at some angle theta, okay, this is going to correspond to an image space, okay, I would just have that, I have something at theta that corresponds to variations that just are perpendicular to that line along theta. Okay, so that's how you know what a Fourier component applies to. And then the magnitude of this vector, this magnitude here is just kx squared plus ky squared. Okay, so that this spacing, this is the frequency, the magnitude of the frequency, and the spacing here is just 1 over f, or let's call this k. Sorry, k. Okay. So that's, as we're doing our sort of examples, just keep that in mind. If I know where I am in K space, I know what pattern it responds to. Okay. So let's take a look at this. So here's K space here. So this is KX, KY. Let's say I take a point along the KX axis, right? So remember, KY is equal to 0. So there's no variation in the Y direction. So this responds to pure variation along the X direction at some frequency, right? Now, what happens if I go out further in K space, right? That means the length of that vector in K space got longer. So 1 over that is going to get smaller. So the further I go out in K space, you notice that this period is getting smaller, right? Which makes sense. Higher spatial frequencies mean that the period gets smaller, okay? And this is along the X direction. If I go along the KY axis, right, and KX is 0 now, then that corresponds to a component where I only have variation in that dimension, the Y dimension. So this is now X and Y, okay? And if I go further out along the KY axis, then the period gets smaller because I have a higher spatial frequency. And now if I go out into some dimension along the kx and ky axis, in this case, like 45 degrees, then that's going to correspond to, I take that vector and I just take the perpendicular to that vector, and that's going to be the variation I get. All right. So that's sort of the basic concepts you need for Fourier transforms. So let's look at this movie here. So this is going to start off by showing you the K space for an image, and we're going to start off with just the center of K space. So the center of K space is those things that vary, don't vary, have very low spatial frequencies. And remember, the center of K space is the overall value of your image. So you sort of see if all I had was the center of K space, I would get this blurry looking image, right? There's some structure to that, but it's mostly just something that you wouldn't want the doctor to perform surgery on you if you just had the center of K space, right? Or just some low frequency. I mean, it's like this this is going to be turn out to be a head, but not knowing it's a head, you don't really even know what body part it is, right? So let's get some more K space. Now at least I know it's a head, right? So I got more details, right? So as I go out in K space, I'm getting more details. I'm filling in those pictures. I'm getting higher spatial frequencies, but still, if they're trying to do like really nice, precise surgery, you're like, oh, I think you need a better picture than this, right? Because like, I mean, this is good enough to like take out your cerebellum, which is this part. At least like if all they had to do was take out a big part of your brain, this would be sufficient. But if they had to go in and sort of pick out like a very small part of your brain, you'd say, well, you need to collect more data. Okay, so let's collect more data. Here we've got about half of K-space. Whoops, stop. All right. Anyways, so essentially once we get all of K-space, you start looking at images that are like, okay, well that's pretty good. You'd feel okay if a doctor had to perform surgery on you with this sort of image. So the question we're going to try to answer in the next few lectures is how much data do you need to collect, right? Because it takes time to collect more data, and time is money. And so there's always going to be this trade-off between um, how much time do you have to collect your image and how much information do you need for diagnostic purposes. And so that's always the trade-off that we're going to look at. So we're going to get at trying to answer that question in terms of how do you design an imaging system such that you get enough information that it's going to be of diagnostic value or of research value. So let's look at some examples. So here is the image on here. This is my base image, and this is its Fourier transform, so the K-space. Okay, and you can sort of see here that what we're going to do is we're going to play a game. We're going to sort of these parts of K-space, we're just going to zero them out. We're going to say, let's get rid of that information. And we're going to do the inverse Fourier transform and see what happens to the image. Okay, and we want to sort of build up our intuition of what K-space does. So this is similar to what you did in your homework. So let's look at this example. So here, if you look at this image, notice how it's got really nice detail, right? I mean, like this edge here is really sharp. You got a really nice delineation of all that variation in your cerebellum, okay? Um, Now let's look at this image here. What's happened to this image? See that where it was really sharp? Now you lost that, right? And this edge that used to be really sharp, it's no longer sharp. But this edge here is still relatively sharp, right? Because we've kept the information about variations going this way, right? But we've lost the information about variations going this way. And so why this edge is still sharp, this edge is still sharp, but this edge is blurry. And because these little details here comprised of edges going both ways also gets blurred out. Okay. So that's sort of showing you trying to build up some intuition of, how different parts of K-space relate to your image. Here's another interesting example. These are called artifacts. And so remember we talked about how like the longer frequency is at like sort of the FM or civil aviation frequency. So every once in a while, there's going to be energy injected into the MRI room. Okay. It can come from inside the room, from just like metal hitting each other, or someone brings in something, or it can come from an outside source. So every once in a while, there's going to be energy injected in K-space where you don't want it. And these you could actually get this on an MRI image. So here, what we've done is we've taken our K-space and we've just added some energy here. Okay. And so this is along the KY axis, right? And so this is going to give you stripes that go like that. So if I reconstruct this image, I'm going to get my original image, but it's also going to have these stripy patterns on it. Okay. And similarly, if the energy was injected here, remember, I draw a line out here and I draw the perpendiculars. And so what I see is those stripy patterns like that. All right. Okay, so this is just sort of showing you what it looks like. So if I'm at some point in K-space, I get these stripy patterns. And remember, underlying all this is representing sort of the orientation of all the spins that are there. And so here we have Kx equals 0, Ky equals 0. So all the spins are pointing in the same direction. Here I have Kx equals 0. So along the x-axis, all the spins have the same orientation, but they're varying along the Ky axis. And so here, let's sort of build up to this. So here I'm looking at, and this is going to be sort of, for the next few slides, this is sort of doing a simple example of what you'll do on your homework, where you're going to have to look at diagrams like this. So let's make sure everyone understands this. So You're going to have to understand, you're going to have to look at patterns like this and say, where are you in K-space? Okay, so let's spend some time on this example. So here you see a pattern like this, right? So you ask yourself, is there any variation along the X direction? No, right? So therefore I must be at Kx equals 0, right? Is there any variation along the Y direction? No. So therefore I'm Ky equals 0. I'm at the center of K-space. Great. Okay. Let's look at the next example over here. Is there any variation along the X direction? Yeah. What's the period of that variation? Assume that this is 1, right? So what's the period of variation along the X direction? So you can take any row and go along that row. How far do you have to go? 4, right? So it's 4, and so the frequency is just 1 over 4. Is that correct? Yeah. 1 over 4 is 0.25. So you're set. Okay. How about the Y direction? Is there any variation there? What's the period? 2, right? And 1 over 2 is 0.5. Okay. So you're all set. Okay. Now here's the tricky part. Here I'm saying Kx equals minus 0.25. Whereas here I had Kx equals 0.25. So what's different about these two guys? One's 0.25 and one's minus 0.25. So how did I know that the one on the, well, how did I know this one had 0.25 and the other one's minus point? Go ahead. Yeah, exactly. So this one here is going clockwise, right? And this one here is going counterclockwise as I go along in the X direction. Okay. And then here we can't really tell because it's going half a, 0.5 is it's going pi each time, so we can't really tell. Okay. And then this one is pretty easy. It's there's no variation in the Y direction, so it's obviously 0, ky. And then it looks the same as this guy here, so it's 0.25. Okay. So you can sort of see that if I give you any pattern of spins, you should be able to sort of tell me where you are in Kx and Ky. And so one of the homework assignments is just going to be to sort of look at, I think, like 9 different patterns, and you just have to say what goes with what. Okay. Okay. So then let's just talk. Well, we're going to end today with just a few more slides on talking about how do we actually get this Fourier information. Okay. So remember, the formula is I'm going to take my object g of xy, right? And I'm going to multiply it by some complex exponential e to the minus j 2 pi kxx plus kyy dx dy. Okay? So it's like taking my image, I'm multiplying it by this pattern, and I just integrate over that. And that gives me, that whole thing gives me one number, and I plop it into my, my computer and say, that's that point in K-space. All right? Then I might go to some other point in K-space where now I have this, notice the object stays the same, right? I'm trying to get information about one object, so I assume the object stays the same. Now, later on, we might have to change that assumption because what if the subject moves, right? But for now, we're assuming my object just stays the same. All I do is I change this pattern, right? I'm just changing my complex exponential. I multiply my object by that exponential, I integrate, and then I take whatever I get out and I plop that into my computer. And that's another point in K-space, right? And so MRI is we just do this process over and over again till we fill up Fourier space. Okay. And once we have enough information, we do the inverse Fourier transform. Question?
How do you know which exponential to use based off of what you want to like correlate to the key base?
Yeah, so that's a good question. So basically, it's going to turn out to be like how many points do we need in K-space, right? So that's going to be like, one question is, what's the spacing? How finely do I need to sample K-space? And also how far out do I need to go in K-space? So we're going to get to that probably in a few lectures. So that's going to be, that becomes a fundamental question of, I know I need these Fourier components, but how many do I need, right? It's much different if I need 1,000 versus a billion versus a trillion, right? So it's not only money, it's also like, human beings can only lie in a scanner for so long, right? So if you come up with a method that says, well, I can give you a really nice image, but it's going to be 24 hours that you have to lie in the magnet, people are like, no way, right? And it's different for an adult than a child, right? Like most adults can lie in the magnet for about an hour, without moving too much. You're not going to get like a 3-year-old kid to lie still for more than like 30 seconds, right? So pediatric imaging can have very different demands than adult imaging, or else you're trying to image something like the heart, right? The heart's moving the whole time. So then there's other questions you have to come into play. Okay, so that's a great question. So we'll get to that. Okay, I think we're at the end of time. So just to review, I guess we'll send out an announcement today to clarify the Project 1 submissions. There will be another pre-lecture quiz posted later today. And I'll stick around here to answer questions if you have any questions. Okay, thanks.